Hey everybody, in this video we're going to talk about applications of vectors. We're going to put some context around these things that have been troubling us so much. So let's start with this big kind of scenario. So we've got the position of a boat A, t hours after it leaves the harbor, given by r sub 1 equals t 30:15. So remember 30:15 is our direction vector. A second boat B is passing near the harbor, and its position vector at time t is given by the equation r sub 2, which equals 55 plus t 10:10. So what we're going to do is, as we look at this, we're going to look at three different situations. We're going to look at A, how far apart the boats are when boat A leaves the harbor. We're going to look at how fast each boat is traveling, and then we're going to look at if the boats are in danger of colliding if one of them does not change course. So real drama in this problem here, right? So we got to make sure that these boats don't crash. All right, so let's start with A. So when we look at A, we are looking at when time is 0, because it's when boat A leaves the harbor. So nothing has happened yet. So t is equal to 0. And our position for A is at the origin. It's at its starting point, 0, 0. And if you look at the equation r sub 1, there is no position vector there because it is 0, 0. So we don't include that in there. And vector B, or boat B, excuse me, is at the position when boat A starts leaving the harbor at 55. So that's that position. So what we're going to do is we're going to try and find the distance between these two things. And so we're going to find the distance from A to B. Now, since A is already at the origin, if we just find the vector of B, we're going from the origin to point B. That's basically our vector, and we can find the magnitude of B, and that will give us just the distance of there. It kind of strips down that direction piece, and it just gives us the distance. So we're going to look for the magnitude of B. So that's going to equal the square root of 50 squared plus 5 squared. So start simplifying this. 2500 plus 25, square root of 2525, which is approximately 50.2. 50.2, we didn't put a distance on here, or a unit, so we'll call it kilometers, let's say. So when this boat A first starts leaving, we know that they're approximately 50.2 kilometers away from each other. Now, how fast is each boat traveling? So we have to now look at our direction vectors. So first, that's going to be 30:15 for our blue, or our r sub 1, and 10:10 for our second boat B, r sub 2. Now, remember, these first ones that we did in part A, they were our position vectors. So now we're looking at the direction vectors, because the direction vectors are basically the same thing as our velocity. And we haven't talked a whole lot about velocity within vectors, so if you have some background knowledge on it, that's going to help. If you don't, you may want to go and check out one of the other videos on velocity. But basically what velocity is the rate of change of the displacement of the object or the boat, or whatever you want to say it is. So the rate of change, so how fast it's changing its placement with reference to a set point. So if we look at the magnitude of the direction vectors, then what we're doing is we are essentially getting rid of this idea of direction. So, because we take the square root of the squared values. So we're getting rid of any positives or negatives in there, and we're just looking at the rate of change. So we're kind of getting rid of that displacement. How are we going this way from our original point? Are we going that way from our original point? So the magnitude is just stripping us down to the rate of change of the velocity, which is the same thing as our speed. So we're going to look at the magnitude of 30:15 for boat A, and that's going to equal square root of 30 squared plus 15 squared, which equals the square root of 900 plus 225, square root of 1125, which is approximately 33.5 what do we got, kilometers per hour, because we're now talking about speed and time. I'm sorry, we're talking about a rate of change, so we've got the kilometers per hour. Then we look at the speed of boat B, which is the magnitude of 1010. So that's going to be the square root of 100, or 10 squared plus 10 squared, which is the square root of 100 plus 100, square root of 200, which simplifies to approximately 14.1 kilometers per hour. So that's how fast each boat is going. Boat B is just kind of sailing along nice and slow. Boat A is on a mission. They're out there going 33.5 kilometers per hour. Okay, so now C, are these boats in danger of colliding if one of them does not change based on the position of boat B and the position of boat A and the speed of A and the speed of B? Will they collide at some point? So if this happens, then there will be a point on these equations, the equations of these vector lines of r sub 1 and r sub 2, there's going to be a point somewhere on there where these two things are equal, and that would be where they collided. So we essentially want to find out, does that point exist? So we're going to look at the component pieces of each of these. We're going to look at the x values and the y values, and we'll see if there is any risk of these things, of these two things being the same and crashing. So let's look at our x components. So r sub 1, the x component is 30t, and the x component of r sub 2 is 50 plus 10t. So if we simplify this and solve for t, then we have 20t equals 50. Just subtracted 10 from both sides. Divide both sides by 20, and we get t equals 5 over 2, or of course 2.5 hours, because t is measured in hours. So in 2.5 hours, whatever our x value is, however far over on our x, that's when we would be hitting that spot where those two equations are the same. So now we need to make sure whether or not the y component is also equal. So we're going to look at that. So the y component of the r sub 1 equation is 15t, and the y component of the boat B, the r sub 2, is 5 plus 10t. So subtract our 10t, we get 5t equals 5, so t equals 1 hour. So at this point, whatever it is, some point somewhere out in the harbor, there's one spot that they will both cross, that both boats will cross. But what's happening is we're seeing that they're going to get there at different times because our times don't match up. The time for our x component does not match with the y component. So since we have those different times, we know then that the boats are not going to collide. They're not in danger of colliding with each other. Now, if those times were exactly the same, if they were both 2.5 or if they were both 1, then we know that it takes the same amount of time to get to that one spot on the x and the y, whatever that displacement is, for both boats to get there at the same time, and then they would crash. But since the times are different, we know that they're not going to collide. So I hope that kind of helps putting some context around the vectors, so that way you can have a little bit more of an idea of why we're doing what we're doing. So again, hope that helps, and we'll talk to you in the next video.